Coming to the next part of this session. Last part we saw the derivation of velocity and the maximum velocity and its ratio. Now here we'll see discharge, the pressure difference, and an additional derivation or term, shear stress distribution. We'll see how those are derived. See, remember in pipe flow I was telling how you will get the discharge value. Discharge value is average velocity into area. So if we multiply the average velocity value with the area, we get discharge. That is Q is equals to U or U average. You can take any, we'll take U bar only, that is U average into area. Here area is T into 1. Why? See, we have, this is the diagram, this is the thickness T, flow is happening this way, area will be this one. If you take it in a three-dimensional view, we are assuming this dimensions to be 1. Since we are taken per unit width. There also, while deriving the velocity distribution, we are taking the width of the element as 1. Here also we will be taking the same variable. So actual discharge will be U bar into T into 1. To find out that, first we have to find the elemental discharge, discharge through the element that we are considered. How will we do that? dq is equals to u. Here u is a function of y. Here we got u as minus 1 by 2 mu into dou p by dou x into ty minus y square, which means u is dependent on y value, which means u is a function of y. So that is why we are using u here. U into area of the element. What is u? Minus 1 by 2 mu into dou p by dou x into ty minus y square. What is the area of element? See, flow is happening this way. If you remember the diagram, this was delta y, right? That was the thickness into 1. This was delta y, this value was 1. So dy into 1. Now we'll integrate it. What should be the limits? Limits is we have taken dy at a distance y from the bottom wall. So if we integrate it till the top wall, that is 0 to t, we'll get the total discharge between these two parallel plates. Q is equals to integral 0 to t dq. This is integral 0 to t minus 1 by 2 mu into dou p by dou x into ty minus y square dy. Take out the constant terms. Minus 1 by 2 mu into, so this is x, dou p by dou x to, what is the integration of ty dy? Ty square by 2, integration of y square, y cube by 3, 0 to t. Final value will be minus 1 by 2 mu into dou p by dou x. What is this value? If I substitute 0, this will anyway be 0. So no need to think about that. If we substitute t, the value will be t cube by 2 minus t cube by 3. That will become t cube by 6. Okay, so into t cube by 6. The final value for discharge is 1 by 12 mu into minus dou p by dou x t cube. This is the final expression for discharge between two parallel plates. Now from this, what can we next derive is average velocity value or mean velocity that we all already discussed in pipe flows. What is average velocity? U bar Q by A. We have Q, this value, and what is area? T into 1. We'll directly write the answer here. It implies U bar is equals to 1 by 12 mu into minus dou P by dou X into T square. Why? Because divided by T, T1 T goes, so it is T square. This is the value for average velocity. Now, what was the expression for maximum velocity? U max is equals to 1 by 8 mu into minus dou P by dou X into T square. So what is the value of U max by U average, U bar? Substitute this 1 by 8 mu into minus dou P by dou X to T square by 1 by 12 mu to minus dou P by dou X to T square. This value, what will we get? Everything goes to P by dou X, P by dou X, T square, mu. So it is 12 by 8 is equals to 3 by 2. Is the value of U max by U. So as usual, as the same way we derived pressure difference per unit length over in pipe flow, we'll be deriving the same thing here also. To derive that, what do we have as our average velocity value? Let me write the heading. Pressure drop now we have average velocity value as U bar is equals to minus 1 by 12 mu into dou P by dou X into T square. It implies dou P by dou X is equals to minus 12 mu U bar by T square. Or to get the pressure difference, what do we do? Del dou P integral 1 to 2 is equals to minus 12 mu U bar by T square dou X integral 1 to 2. What do we get? P2 minus P1 is equals to minus 12 mu U bar by T square into X2 minus X1. If we assume we are taking it from the entry to the pipeline, that is entry to these both plates and to their exit, this X2 minus X2 will become the length of the pipe. See, this is if this is the parallel plates that we considered earlier. If we consider point 1 here and point 2 here, then the distance between these two will be equals to length. So we can write this value as length also. So P2 minus P1 is equals to minus 12 mu U bar by T square into L. If we take out the minus sign here, we'll take this over here. So P1 minus P2 is equals to 12 mu U bar L by T square. This is the final expression for pressure drop for given length for a flow between parallel plates. Important one. let's go to the next segment. This is actually an additional segment over here, but very easy to derive, not a big thing. Shear stress distribution. Shear stress distribution. So we know tau is equals to mu dou u by dou y. What is the value of u? Mu dou by dou y into minus 1 by 2 mu dou p by dou x into ty minus y square. We take out the constant terms. These are the constant terms. So tau is equals to mu into minus 1 by 2 mu dou p by dou x into dou by dou y of ty minus y square. What is t minus 2y? This mu goes. We have tau is equals to minus 1 by 2 dou p by dou x into t minus 2y. This is the expression for tau at a particular point where the distance is y from the bottommost plate. Here you can see tau varies with only y, whereas u varies with y square. Hence it's the same thing. Tau is linear variation, whereas u is parabolic variation. Now from here, if we want to derive the maximum shear stress value, we'll apply y is equals to 0. Why? At the wall shear stress is maximum. So let us apply y is equals to 0. Tau will be tau naught is equals to minus 1 by 2 into dou p by dou x into t. This is the expression for maximum shear stress value. So thereabout ends the topic flow between parallel plates when both the plates are at rest. There is another adjoining topic to this, that is flow between parallel plates when one plate is moving with a velocity v, or it is also called as co-ed flow. I plan to give that topic as an assignment. The announcement regarding that will be made soon in either WhatsApp and in Google Classroom also. So the next topic I will be uploading video would be hydrodynamically smooth and rough surface and turbulent flow introduction. Thank you.